When nuclear reactions occur, they occur using a timing called half-lives. And we're going to look at how time affects radioactive isotopes. The half-life is important because drugs are eliminated from the body, decompose in the body, according to half-lives also. So if you understand the half-life of isotopes, you will understand the half-life of drugs and how they're eliminated from your body. Let's go look at this example here to try to understand what a half-life is. If you have 16 grams of phosphorus 32, in 14 days, what you will find is that only 8 grams of phosphorus 32 remains. The rest of it has been changed into sulfur 32. This 14 days is called the half-life, and this is the amount of time it takes for a sample to decompose or decay halfway. If I have another 14 days elapse, that it's not that the other half is gone, but what happens is half of what remains at the beginning of the 14 days will be remaining. So 16 grams goes to 8 grams in one half-life. Then 8 grams goes to 4 grams in one half-life. When another half-life occurs, only half of that 4 grams is left, so 2 grams is there. And if another 14 days were to elapse, there'd only be 1 gram of phosphorus 32, and on and on and on. This half-life is independent of temperature, pressure, the amount of the sample. It's every time you find it decomposes, half remains after that half-life expires. Now, 14 days is not the half-life of every isotope. That's only the half-life for phosphorus 32. If you had another radioactive isotope of phosphorus, it would have a different half-life. And any nuclide in the periodic table has its own particular half-life. You have to either experimentally determine them or look them up in tables. But they stay steady according to whatever nuclide you have. Let's look at an example. Iodine 31 has a half-life of 8 days. How much of a 100 milligram sample will be remaining after 32 days? Well, the first thing you do is you figure out how many half-lives is 32 days. 32 is 8 times 4, so that must be 4 half-lives. So what happens after one half-life? 8 days. 50 milligrams is left. After 16 days, that's 2 half-lives, so there's only 25 milligrams left. After 24 days, well, there's half of 25 left, so 12.5 milligrams. After 32 days, that's 4 half-lives, so that's only 6.25 milligrams. Let's see an easy way to figure this out. 100 milligrams goes through 4 half-lives, so you cut it in half 4 times by multiplying by 1/2 4 times, and you end up getting 6.25, just the same way I went through it with you before. You go ahead and try to do the same problem, the same type problem. Positron emission tomography, this is what's called PET or PET scanning. It uses a positron emitter like fluorine-17. Fluorine-17 has a half-life of 110 minutes. If you have 0.25 grams of fluorine-17, how much of the fluorine labeled estrogen is remaining after 5.5 hours? Try the problem after you pause and then restart to check your answer. Well, 5.5 hours is 330 minutes. You divide that by 110 and that's 3 half-lives. 0.25 grams multiplied by 1/2 3 times gives you 0.031 grams. That's what's remaining after 5.5 hours. Uh, let's look at some of the other type of reactions. We have nuclear fission. In nuclear fission, what you have is a big nuclide decomposes to two smaller nuclei. A lot of times you have to hit it with something like a neutron. Well, let's see what happens. It's all going to balance. 235 plus 1 gives you, what's the sum over here? 91 plus 142 plus 1, well, that is going to be 236, which is the same sum over here. 92 plus 0 is 92. 36 plus 56 is also 92, so this is balanced. The most I'm going to ask you to do here is either identify a nuclear fission reaction or find the missing particle. There's something called nuclear fusion. In nuclear fusion, what happens is two small nuclei combine to make a bigger one. This example here shows this. Here we have hydrogen 2 and hydrogen 3. They undergo fusion. This is what happens in the sun. So a mass of 5 and a mass of 2 adds up to a mass of 5 and a charge of 2. This is a charge of 2 there, not a mass of 2. Okay, do you see that you have two small nuclei combining to form one bigger nuclei? And of course there's a neutron that comes out. Neutrons are all over the place and you'll see them in reactions, and we kind of ignore them to identify the type of reaction. They're important for balancing, but to identify what's happening, just look at the atoms. It only can occur, fusion only occurs at temperatures like that are in the sun and a pressure like what's in the sun. So we don't do this here on Earth. They're trying real hard to do what's called cold fusion, but they haven't been successful yet. So we haven't been able to do this on Earth yet. Okay, go ahead and balance these reactions using just the same technique that you did before, but in addition, identify the type of nuclear reaction. Okay, the first thing we have to do is fill in the parts of the information that we can get from either our knowledge or the periodic table. So we put in a 1 and 0 for the mass of a neutron. 134 plus 107 plus 3, because there's 3 of these, this must be 1 and 0. 53 and 42 for the iodine and the molybdenum. They add up to 95. 95 gives you americium as the element. Okay, down here we need to say that an atomic number of hydrogen, for hydrogen is 1, for helium is 2, and a proton has a mass of 1 and a charge of 1. So 4 plus 1 is equal to 2 plus 3. 1 is equal to 1 plus something is equal to 2 plus 1, so this is 3 and 2. That's helium. Remember to do problems. Do all the online homework so that you can earn all your points, and also that you learn from doing the online homework. Do end of chapter problems if you have to, but be sure to do the worksheets that are posted for this chapter, because those will help you be successful in the exam.